And essentially, it tells us that momentum is a particle exchange momentum in the direction of velocity, and they also transfer momentum themselves. But there is also a part which is related to transversal, also longitudinal too, but there is also a tangential transverse of momentum which leads to diffusion. And this equation conserves momentum. So if it has a form of continuity equation, but if you write an equation for the energy density, it's again has this form of a flux of energy, which is a rho v squared over 2 plus p. This is the kinetic energy transported. It's like potential energy pressure slides. It also has this sigma v term, but it has an extra term which is plus eta, which is dynamical viscosity sigma ik dvi over dxk. And if you recall that this is a symmetric tensor, which is by itself proportional to dvi over dxk plus dvk over dxy. So if you integrate over space the energy time derivative, you will get minus which is a non-negative term, and so essentially what diffusion of momentum does, it preserves the translation invariance in space, it preserves space homogeneity, which means it preserves conservation of momentum, but it breaks time reversibility and it breaks energy conservation. Okay, so this is an important point, and now we have this equation, and it's difficult. Right? So it's nonlinear, and it's second-order partial differential equation. So as I said, so here we continue. Aren't that many solutions? In particular, they are very easy to obtain a solution in which v is perpendicular to grad v, in a sense that velocity is, for example, unidirectional, and it changes along a transversal coordinate. And the first example is just a flow of a fluid over the inclined plane, let's say, as a model of a river or puddle. So we assume that there is a layer of a fluid, and it has, let's put our axis this way, and this would be its depth, and there is a gravity acting like this. So in our equation, what we'll get two components of this equation. First of all, we have dp dz would be rho g sine alpha, and we'll have this would be z projection, and that would be x projection, and we assume that pressure does not change along this. This is a uniform thing. So what we will have, we have v in the direction x. We have new term, right? And it will be equal to what it will be g cosine alpha. So this is the, and alpha will be this angle. Okay, so that's more or less two simple equation. As you probably notice, they are linear because a nonlinear term exactly identically zero. So let me write this. And of course, you need to satisfy boundary conditions that the velocity is zero here, but the stress here is just pure pressure. So whatever atmospheric pressure you have, here stresses must have only normal component. So here's the solution. It's pretty simple. V depends only on z. It's rho, it's g sine alpha divided by 2 nu z 2h minus z. And let's just check it for a kind of sanity check. So let's take first a puddle, something pretty thin. Let's say h is 1 millimeter, 10 minus 1 centimeter. G is, again, in centimeters, 10 to 3 centimeters per second squared. And let me remind you that nu for water is 10 minus 2 centimeter squared per second. Okay. Now, if you plug here 10 to 3, yeah, we need to take alpha. So what is the typical pavement? Well, kind of 10 minus 2. Well, if you aren't, well, there are many hills here in Stony Brook, which is essentially 20 degrees. But then it's clear, then water just flows very fast. But let's just take alpha pretty small like this. So what will we get? We get, in this case, 10 to 3, 10 minus 2. This would give me 10 to 2, right? This is z square and h square, and this is 10 minus 2, and let's say 1/2. Okay, so it's 2, 2. So it's like 5 centimeters per second. It's pretty reasonable. It makes sense, right?
What are the boundary conditions?
The boundary condition is that velocity is 0 at the bottom, and that the stress at the surface is only normal because it's equal to the outside pressure, which does not enter it. You can assume that there is vacuum up there. So in a sense, when you look at this solution, it has 0 at z equal to 0 and has its derivative, which is stress 0 at the upper. So your tangential stress is 0. Okay. Now let's consider river. Well, again, a slow river on a plane. Let's take normally, I don't know, for Mississippi, I guess it's something like the boundary condition here is dvx dvz equal to 0 at z equal to h and v of 0 equal to 0. There are two boundary conditions. Okay. So if you look here, you see that your derivative at h is equal to 0 and velocity itself is equal to 0. Okay. It's a profile like this.
It's because in this case it's pressureless, right?
Because in this case, well, if you put here pressure, it has no influence on it. This is a condition that tangential stress is 0 on a boundary. So there is, if there would be other fluid over there, it would support tangential stresses. But you assume that it's either vacuum or air, which density is 10 minus 3. So you don't support. So your tangential, this is your x, this is sigma xz. What do you mean? It's not a transfer. It's just a statement that the flux of momentum is 0 on this surface.
Why? In real life, you just transfer.
Because it cannot assume it's vacuum there. Assume that there is vacuum here. Well, it transfers momentum to the air, but it's negligible because air density is small. Assume it's vacuum. So it's, it's Mississippi in the vacuum. Well, puddle. But okay, you can account for it. It would give you something of order 10 minus 3 correction because the ratio between density of water and density of the air would stand there. But you're right. I mean, in principle, if you have something flowing, then air starts moving, and your steady state is kind of involved moving air. Okay, let's just use this formula for a river, and we'll take even normally it's 100 meters per 100 kilometers. It's really kind of 10 minus 4. Well, sometimes 10 minus 3, but plain rivers are like this. Well, h typically is like 10 meters, which means 10 to 3 centimeters. kind of a normal river, and that's all. The rest is the same. So essentially, we take alpha extra 10 minus 2, but we take h instead of 10 minus 1, we add 4 orders of magnitude here, and it's squared. It adds you 8 orders of magnitude minus 4, it adds you 4 orders of magnitude. So you will get something like 50 kilometers per second. It's the solution of this equation, just as it is. Kilometers per second. It's a bit fast, yeah. It's a bit fast. So again, we are in the 19th century. We just happily derive this equation. We plug the numbers that we definitely know absolutely true. You know, we know G. You know, we know viscosity of water. We get this answer. What we have to do? Like Feynman used to joke, these people spent 100 years solving equation for dry water. Okay, so we have trouble, and this trouble need to be, and apparently it's a big trouble, right? So you may say, so what is, first of all, the difference between why it works here and it does not work here? Well, we say, look, if I would look at the naively defined Reynolds number, which is my typical velocity times my typical scale divided by nu, then apparently these two situations are very different, right? Because, well, my u by many orders of magnitude larger and my h by many orders larger. But the problem is that naively Reynolds number doesn't make sense for such flow, because the Reynolds number is a ratio of nonlinear term to a viscous term, and nonlinear term is identically 0 here. And it's 0 because we assume something very, very strong. We assume unidirectional flow, which means that we assume totally smooth and flat bottom, right? Which means that if we say, I mean, look, real rivers, they are always kind of, you know, having something like inclination, okay? So let's say, okay, let's be a little bit more realistic. Assume that we have kind of another angle which we would call beta, right? And so we say that this would be, and this beta would make our nonlinear term non-zero, because when I do v grad v, that would be like u squared over h times beta. Beta would be my actually misalignment between u and grad u. So in this case, I would really need to use beta. And now it makes sense. So I may compare this, which would give me something with, well, I plug all the numbers like 50 beta and river. This is first my paddle, and second my river. This would give me 10 to 12 beta. So apparently, this must be extremely sensitive to whatever is on the bottom, and it's clear that we really need to understand, because at this point I cannot safely use this solution, because whatever misalignment would be immediately triggering this term. Okay?
So that means even one atom.
Well, look, I intentionally took a kind of, but you know, 10 meters river with this pretty realistic thing. Which means that all these numbers, which tell you one thing, this does not make sense. It does not make sense in any way you try to interpret it. And in one way that you understand that your assumption are unrealistic is its inhomogeneity. So what I'm essentially trying to illustrate is that an attempt which people spent 19th century solving this equation and finding different particular solution, in particularly in 2D, when you look at this equation, it's really kind of, there's a lot of beautiful mathematics you can use. So what now we'll do, I suggest, that we try to do what physicists always do. We take the equation, we go to one limit, we solve it there, just totally one limit. Very large Reynolds number, very small. Then we go to other limit, and then we try to match them. Okay, so that's kind of a strategy, which again turns surprisingly difficult here. So we have a nonlinear equation of second order. So there are two difficulties here. This, which would be disappearing at very low Reynolds number when viscosity is very large and we can neglect it, and this, which is a higher derivative, and it will be disappearing at very high Reynolds number when nu going to 0. Because this is a graduate kind of mini course, how would you start? Which thing you think is easier to do? Large Reynolds number dropping second derivative, or small Reynolds number dropping nonlinear term? What is more trouble? Yeah.
First one.
Huh?
I think that's the small Reynolds number and dropping the nonlinear term would be easier.
Okay. Any other idea?
I think dropping the second derivative would be solved.
Okay. So you aren't afraid of nonlinearity, but you aren't afraid of high derivatives. Again, it's mathematically well, of course, having a linear equation is nice because you can use superposition principle, right? But on the other hand, when you drop the second derivative term, what this gentleman suggests, you get much more symmetries in your equation, because this second derivative term is this diffusive term, which breaks kind of many symmetries. And essentially, people in the 19th century went this way. They initially dropped this, even though they already, since Navier, they knew about the viscous term, they dropped it and they worked with what is called ideal fluid. And now we'll do this, and then we'll see, and then we'll go to the other limit, which will be Stokes limit, and then we'll see what's in between. So let's solve now a problem in which at least there aren't unidirectional flow, but geometrically the simplest, a sphere, right? So I have a sphere, and which uniformly moves, or well, my spheres are always non-spherical. Let's think of a simple physical situation for which, because before solving problem, let's motivate ourselves. I take a bubble. Okay, so you have a Coca-Cola or champagne, whatever you prefer, right? And it's under the action of forces. What forces act on an air bubble in a liquid? Buoyancy. What is buoyancy? Is the weight of a displaced fluid. Okay. Now its mass is the mass of the air inside. And air has density which is 1,000 times less than the density of the water. So if you kind of look at it naively, you say, okay, its weight is the weight of the air, but the force is the weight of a displaced water. So my acceleration must be 1,000 g. 1,000 g is also like, it's not 10 to 12. It's not speed of light. We're still safely non-relativistic, but it's idiotic. So before solving it, I mean, just this, what is wrong in this simple argument that... Yeah, I guess.
The answer was if it goes up in acceleration 2g.
Yeah,
Correct.
which we will receive in 10 minutes. But qualitatively, what's wrong with this simple statement that you just take a force? Buoyancy force is just a sum of a pressure acting off it. So pressure from below is higher than pressure above. That's Archimedes force, right? And divided by the mass of the area, and this is an idiotic answer. Why? If it will be true, it would just throw a fluid, No.
Isn't the mass inside the bubble is not the same?
The mass inside the bubble is mass of the air. Inside is air, trust me.
So the buoyancy force doesn't work, and you by that argument you neglect the motion of water.
Yeah. So when the bubble starts to move, it's not only air that you move water, right?
Yeah.
So if you look at this force, it must be time derivative not only of the momentum of the air inside, but also momentum of the fluid. Right? Right? Wrong. Why? Because let's imagine that it's really closed bottle, right? So there is walls, and momentum of liquid inside is identically zero all the time because it's a closed system. A bubble moves there, whatever. This momentum is zero.
Yeah, but I say it works, so it's the energy.
forces are always time derivative of a momentum. Or
Drag.
we neglected viscosity for now, but okay, if you say that you have this g, right, acceleration, and you ask how much viscosity, because viscosity force is 0, because your velocity is 0. We computed at the initial moment. You may compute at what velocity viscous drag would stop it. I can give you an answer, 100 meters, 50 meters per second, which there will be no sparkling water, you know, in that case, and no beer for us. Okay, so that's always kind of, you know, motivation, because when we finish this, what we will realize that you are right. Indeed, the acceleration is 2g and not 1000g. It's because when the bubble moves, it moves approximately the amount of water, which is half of the displaced mass. That's why it's 2g. But what is the force? It's ddt, not of momentum, but of quasi-momentum. And so we learn difference between momentum and quasi-momentum. Okay, let's go. So the beauty, so now what we'll be doing, we'll be neglecting this term, right? And then one can prove a very beautiful theorem, which is a conservation law. So I'm starting now, not immediately solving this problem. I'm giving you, you know, like on one leg, introduction into ideal fluid theory. And it starts from a very beautiful statement, which is a new type of conservation law. We already seen conservation laws like continuity equation, on we see Lagrangian conservation law like ddt along the motion is changed, but there is another conservation law which is non-local. So if you take a circulation of velocity along any closed contour, okay, and do ddt of it, which is incidentally a flux by Stokes theorem, it's a flux of vorticity. You remember omega is the curl of V. So if I take VDL, of course there are two terms. There is a dV dt integral, it's a scalar product here, so it's circulation, plus V dL dt. Well, this is easy because this is essentially dV. It's an integral of a total derivative. Here it's a little bit more tricky. Now I need to account that it's a grad P minus, right? I'm an incompressible fluid. This is my dV dt. All this term, right? It's a material derivative. But then again, an integral of a circle I can turn into integral of a curl over the surface, but curl of a gradient is 0. So this is 0. It tells me that vorticity of any contour, a flux of vorticity through it, is conserved, or circulation of velocity. It's not a conservation of angular momentum. It looks like it's angular momentum, but it's a non-local conservation law. It does not have a local density. It's not V times R integral. This angular momentum has a local density like this, but it is not. Okay? But what it tells you something very beautiful, that if your flow initially was curl-free, it will be curl-free forever. If you consider, for example, this case, yes, Zohar?
The contour that's moving.
It's a liquid contour, yeah, which means that the contour changes with the flow, yeah. Which essentially tells you that if you kind of expand your contour, your vorticity drops. If you contract your contour, your vorticity increases, because the flux of vorticity through this contour is conserved. But it tells you that if you, for example, have a situation for which far away, I'm now turning, so it's my, so I have a, let's say, flow, I'm in the reference frame of my body, which means that at infinity, and I've chosen it in x direction, I have a uniform flow. Uniform flow has zero vorticity. Zero vorticity, it's a beauty, because now I can assume my flow potential. This is technically why ideal fluid is easier, and earlier already realized it, easier than viscous, because you have vorticity conserved, and if vorticity is 0, then it's 0 forever, then you from vector equation go to scalar equation. So essentially, you have this equation, and now you can look at your ddt of grad phi plus, you can write it, so you can immediately integrate this equation and obtain what is called a strong form of Bernoulli's theorem, namely that d phi dt plus v squared over 2 plus p, well, it's p over rho, but my rho is unity, right, is equal to constant throughout the fluid. And you can always include this constant into phi because the gradient of it will be 0. It's a very strong statement. It means that you get v, and then you get p just like this, okay? So what you need to find a potential, then you differentiate it over coordinates, you get velocity, and then you get pressure just by algebraic formula. How to get potential? Well, we are in an incompressible fluid. And now we understand why people spent happily all the 19th century solving this equation, because that's what they were doing everywhere. They were doing electrostatics, electromagnetism, they were doing many, many things, solving Laplace equation. And unfortunately, in this case, it gives you something. Anyway, so here it is. I have a sphere with a radius r. This is u. Or I'm in reference frame of a fluid, I would have my sphere moving with the velocity u. So what is phi? It must satisfy Laplace equal to 0 equation. And another condition is that on the surface of the sphere in this reference frame, velocity will be 0 everywhere, normal velocity. And in the reference frame of still water, the velocity on the surface of a moving sphere will be u. So it means that your v of r equal to r on this surface will be equal to u. So you have linear equation and a linear boundary condition. So your solution phi need to be a linear function of u, right? But it's a scalar and u is a vector, which tells you immediately which of the multiples. So solution of Laplace equation are 1 over r and all its derivatives, and all its gradients, right, multiples. So which one we need to take? There is 1 over r, grad 1 over r, grad 1 over r. We need to make a scalar out of a vector. How to, yes? Somebody knows how to make a scalar out of a vector solving Laplace equation? Huh? Dipole. Okay, so it must be u grad 1 over r, phi of r, with unknown constant. Okay, and to spare you the simple algebra, I can give you Stokes did it at his PhD. That was his PhD result. So you can get it. Phi is r cube u times n, where n is a unit vector. So somewhere n is r divided by r modulus. So it's u cosine theta, if you call this, you can call this theta, and divided by 2r cube. No, phi is by 2r squared. So it's a dipole field, and you can write velocity, which should be electric field of a dipole, usual stuff. Now, what I can do, I can get my pressure, which means that I need to compute velocity, substitute into this formula, and then plug it into a force. If I want to receive what is the force, let's say my F in the direction of x will be integral of pressure cosine theta d area. Okay?
Bubble is fixed.
I'm now working in the reference frame. This is written in the reference frame where, which is attached to the bubble. Okay, this is a very good question, which is immediately will be clear why. So what I now ask you in this formula, pressure is equal to if I take this term, could it give me a non-zero contribution into this force? It's a dipole field. As a dipole field, it has a kind of this point and this point, theta minus theta. They have a symmetry or anti-symmetry depending on components. But V squared will be the same. So if you are interested in the force will be disbalanced between this point and that point, this point and that point, okay? So this gives me no contribution. That's why I'm not even computing it, right? I don't need it. So where the force comes from? Zohar, just ask a right question which tells us where the force comes from. Well, if not from here, then from here, right? But this is time derivative. Where times come here? Look, this is instantaneous equation. I did not solve any ddt equal to whatever. I solved equation Laplace phi equal to 0. That's the beauty of ideal fluid mechanics. It's totally electrostatics. You solve Laplace phi equal to 0, then you get pressure, then you know everything. But pressure contains this d phi dt. And that's what Zohar asked, in which reference frame we are working? We're working in a reference frame of the body, right? So what stands here is this one, right? And for the heck of it, this is also could be time dependent.
You're assuming it's moving at constant speed.
I'm not yet, okay? So what I'm saying is that indeed, if I'm accelerating, then this would be time dependent, and this could be time dependent because I could be shrinking or expanding, and this also time dependent because I'm in a comoving reference frame.
General motion, don't you have to put r minus u?
Here is r minus, that's what I'm saying, yeah.
No, but if it is a function of t.
Yeah. Actually, you need to be like this, okay? But here, what stands here is r at a given moment. Your potential at a given moment of time, actually, this is unimportant, incidentally. When you differentiate it, it would also give you symmetric contribution. What is important is this one, okay? So that your potential instantaneously depends on your cube of your radius and of your velocity.
But in the equation between them, second equation, r minus ut, why don't you have the position that you transform to a new reference frame, and the new r is like r prime equals r minus
here is that if you write it for any particle, that it's this position at a given instant of time, which in principle, if you really want to express it through your previous history of u, you need to solve the equation. But at a given moment, it is just like this. And this is unimportant. This is important.
With the logic, you're assuming that the Navier-Stokes equation or Euler equation, whatever, takes the same functional form.
Of course.
Which is not true.
Of course.
But it's not true. It only has the Lilian invariance. It doesn't have general invariance.
No. Well, at this moment, what I'm doing is incompressible fluid. In incompressible fluid, speed of sound is infinite, which means that I am at any given moment. You see, to get a velocity, I solve equation in which there is no time whatsoever. And this is, of course, consequence of the fact that I'm incompressible. Otherwise, because this is incompressibility condition, right? In this case, I can really solve it instantaneously. Otherwise, of course, it's much more complicated. So this is a very special situation of ideal incompressible fluid where equation for it's just an instantaneous position of my body, instantaneously set velocity in the whole space. That's it. When I have this body moving, instantaneously velocity field in the whole space will be changing according to the new position.
Larger variance under general coordinate transformations.
Well, in a sense that if you'll be moving your body by arbitrary law, imagine that you apply force and you move your body by arbitrary law. At every moment of time, its position instantaneously determines a field everywhere. That's incompressible fluid. Yeah, yeah. Okay, so now when you plug all this into this formula, and again I spare a standard deviation, what you get is the following thing. Okay, so now this is I just, I took this, I integrated over this angle, it's in 3D, so I get this, this would give you 2 pi over 3. So what we see over here is that first of all, my force is proportional to the time derivative of this product. Density of a fluid outside, but if it's just simultaneously, it's 2 pi over 3, not 4 pi over 3. So it's a half of a displaced volume, but it's rho of liquid, okay? Which means that if now I say that this is equal to g, then it would give you that my acceleration du dt, if r does not change. Well, g times 4 pi over 3 rho r cube. This is my Archimedes force. This is my inertia of. So first of all, this is the first example of renormalization in physics. This is a renormalization of mass, apparently, that your bubble of vacuum moves in a fluid, and because it moves in a fluid, it acquires a mass. It's called induced mass, added mass. This is the renormalization. This mass for a sphere is half of displaced volume. For a needle, it will be much less than displaced volume, and for a disk, it will be more. So it depends on the geometry, okay? And in particular, it gives you this to G. But it tells you more interesting things, that the fact that it's d phi dt means that you can get a force out of changing r. Before this, I went swimming, and when you do breaststroke, when you suddenly decrease your area, when you are, that's what octopus is very good in doing. You get an acceleration forward. Why? So you move with a constant speed, then you shrink, and then that immediately makes you accelerating. That's what this formula tells you. Okay? Because forces that act on you is a distribution of pressure of your surface. When you change your shape, you change the distribution on your surface, right? So that means that when you you do this, and then when you go into glide stage, do it fast, right? Because it's ddt of it, which matters. Okay. So first of all, we've got the force. This force is acceleration. It tells us that fortunately our bubble has inertia, and this inertia is finite. Now, as I said, this is not ddt of momentum, right? Because again, momentum depends on boundary conditions. If I include it into some vessel with non-moving walls, then my momentum is 0, right? And this is something which is related to the flow kind of around my area. And I'm really, I need like half an hour for this derivation, so I'll give you now kind of a broken line, and you can look in the book how actually one can prove that this integral is equal ddt of a quantity which is called quasi-momentum. And the quasi-momentum is difference from momentum. First of all, what is quasi-momentum? By definition, we usually meet it in solid-state physics, and we think that this is something which belongs in solid-state physics. And the conservation of this quantity is something different from a conservation of momentum. What symmetry corresponds conservation of momentum? Translational invariance in space, right? So I take my system, I move it in space in a different position, and I claim that it's the same. What symmetry is the conservation of quasi-momentum corresponds to? What's your solid state physics, you remember? What symmetry we use there to get conservation of quasi-momentum, and the very idea of quasi-momentum as a generator?
Discrete translation?
In crystal, it's discrete, but we are in a continuous medium, which means that it will be also continuous. The difference between momentum and quasi-momentum, not that one is continuous and another is discrete. This one will be continuous too. But what translation we do? When we conserve momentum, we translate the system. When we conserve quasi-momentum, we claim invariance of different points of the medium. Okay? So we say that if I shift in my lattice to the next atom, it will be the same lattice. But now, in a continuous media, it will be continuous shift, which essentially tells me the following thing, that I want ddt to be conserved because my Hamiltonian depends on some momenta and of some coordinate, and they depend on some extra parameter, which in this case will be coordinate. I need a medium for this. It's a claim of identity of a medium inside. So there will be extra parameter, and quasi-momentum time derivative must be x derivative of my, and it's a vector, right? Then it is conserved. And for fluid, where my momentum is rho v, now I consider it now as a particles, right? So I have v, which depends on some initial position and time. This is initial position, sometimes also called marker or Lagrangian coordinate. This is my momentum, and my q, my coordinate, is r of my, again, dr dt is v. So r is not a coordinate in space. It's a coordinate of a fluid particle, which is derivative is v, which gives me my momentum, minus its initial position. Or if you want, it's rt minus r of 0. When we did phonons in solid state, we consider displacement of the atoms. It is this coordinate. We were actually using Lagrangian coordinate. Now, you can show that if you need to define quantity for which time derivative is a derivative over x of your Hamiltonian, then is this quantity, just let me write the formula. It will be, in this particular case, k is rho dr v vi, it's a vector delta ij minus dr I over drj. You see? So this is something, and this is the momentum. This is rho v integral over space. This is the total momentum of a fluid. But this is something which includes this transformation. Again, I'm not proving this, you just look at it, but I really think that it's worth mentioning because it somehow tells you where this renormalization comes from. It comes out of this quantity. So what it does, that this integral converges at infinity. Because generally, when you look at this solution, phi, it's a dipole. So its velocity is 1 over r cubed. So if you want to compute momentum, you need to integrate it. It's a three-dimensional solution. It will be logarithmically diverging. Or in other terms, it will be depending on the shape. Quasi-momentum does not depend. It has this minus. So at very large distances, this is delta ij. The particle do not move by your body. So this is something which describes a localized flow around your body, and it's time derivative of this quantity, which is equal to this integral. Okay? Questions? This is an important part. Yes?
Sorry, could you explain again? Confused. What exactly is quasi-momentum?
What I'm saying is that I have a Hamiltonian description of my system, which means that I have momenta and I have coordinates. The only thing that apart from depending on time, usually I have momenta depending on time and coordinates depending on time. I have an extra marker, which is this. It's the initial position of my particle. In a sense, it's a marker of a particle of a liquid, right? So, I mean, this fluid particle, that fluid particle, by the way, Kelvin's theorem is also symmetry which is responsible for it. It's a relabeling of these labels. Those are labels, which means a long ago, all my fluid particle was standing in a row, no flow. I marked each one of them by this coordinate. The statement, the symmetry which I'm using now, is that my Hamiltonian ddx xi is, I mean, in this case, this would be this ri, is 0. Okay? So the derivative of my Hamiltonian with respect to this label is 0, which means that I'm claiming that all fluid particles are the same. It's not the claim that all points in space are the same. That would give me momentum. A claim that all fluid particles are the same will give me quasi-momentum. Okay? So now, and I'm not doing computation, but you check it in the book. Now, if I require this, then this is a quantity which satisfies it. Okay? So ddt of it is equal to ddx ddr of Hamiltonian, which means that it indeed its conservation corresponds to it. Now, if I now compute this in an area in which I have a body moving, then ddt of this exactly will be equal to this integral of pressure. So the force acting of a body, it's a ddt of a quasi-momentum of the fluid, which is finite, and give me mass renormalization. Okay? That's Landau-Lifshitz, excellent book, fantastic book. Did not get it right. It's very badly written at this point, right? It's tried to argue through any Peierls. Peierls actually was friend of Landau. I'm really surprised that Peierls never explained to Landau this right way of presentation, because in Peierls' book it is this right way. Okay? So that's what I wanted to get out of ideal fluid. And now I want to move to the, if there are no questions. This is a non-trivial point. Yes?
Go ahead.
So why should the force be equal to this thing?
I definitely have the forces. I mean, this is a computation, right? So in a sense, I can just not do it. I mean, this is my computation, but this is a way of interpretation. I want to interpret it. I see that my force is ddt of something, right? This something looks like half of a displaced fluid, right? Or I can do it for different shape. It would be third of a displaced fluid. And I'm saying, well, this force is usually is ddt of some momentum. The answer is no. It's not ddt of momentum. Momentum depends on boundary condition at infinity, and this definitely does not depend on boundary condition at infinity. So I'm asking, what is this ddt of what? And I answer, it's ddt of this. And then I ask, what is this? And I say, if you don't have a body, this quantity is conserved by a symmetry which is different from translation invariance. It's a symmetry which is identity of material points. And that explains you why in solid state physics it's a discrete thing. Because there you have atoms which are in discrete positions. So your invariance, you need to discretely jump from particle to particle. Here it's arbitrary. This is a continuous coordinate which is a marker of your fluid particle. Question?
To like try and synthesize the whole thing, because we want to understand the behavior of this bubble, we want to force for a bubble, which that's dependent on pressure. We integrate that, we have that term on this board, which as you said, looks like half for the displaced volume. But to understand that, that's why we go here to get the quasi-momentum. Is that it?
Yeah, half, it's just a consequence of that I consider spherical geometry. Consider a disk, and it will be not half, it will be much more, right? So what is important here is that my force is always integral of pressure over area, because I neglected viscous stresses. All my stresses are pressure. So I need to get pressure. When I get pressure, I find out that this is what matters here. That's why what I do is actually receive. I receive renormalization of inertia. It's ddt of something, right? And then when I'm now trying to interpret it, I'm asking, what is this? So in a sense, let me put it this way. A sum of a momentum of my body and something else must be constant. But this something else is not a momentum of the fluid. It's a quasi-momentum of the fluid. So if you have a body moving in a medium, and of course, Higgs phenomenon grows from here. This is the first mass renormalization. This is a statement that you move something inside a field and you get extra. In this case, you get extra inertia. Okay?
So it's bigger than 1, or it's just
What do you mean coefficient always bigger than 1? Which one? This one? Oh no.
if you get the fraction of the displaced volume,
Absolutely not.
it always must be.
Take a needle and take a disk. In one case it's larger than 1, in other cases smaller than 1. There is no statement here. Your displaced fluid could be, your added mass could be much, much larger than the displaced fluid, which is a disk. Disk is very thin, but its added mass is almost the same. I don't remember now coefficient, but like half of what is for sphere.
Your displaced mass is bigger than, if the effective mass is bigger than the fluid,
Disk.
it's not going to go up, no?
It just would mean, for example, that if you would have an air bubble of the shape of a disk, then its added mass is much larger than the displaced mass, which means that its acceleration will be much, much less than g, not 2g. Okay? Because the disk is really thin, but from the point of a fluid, it pushes about the same amount of fluid as a sphere. You see? Because essentially it's a question how much fluid you push. But a needle is an opposite case. In this case, your displaced mass is much, much larger than your moving mass. Okay? You can create a very, very long needle, so it displaces a lot of fluid, but it moves almost. So there is no, it's all geometry here, right? So there is no kind of, it's just, it's like 50g or it's 1 over 50g acceleration of. But now go and get a bubble of the shape of a disk. So that surface tension would not let you do this. Yeah, that's absolutely right. Okay, we've got it, right? So we've finished in, I actually wanted to give you a little bit of viscous fluid. So, but we did ideal hydrodynamic relatively fast. So now, what may be, I don't want to now then move because I have 5 minutes, and I don't want in 5 minutes to tell you everything you need to know about viscous fluid because there are a lot of there is some kind of a gauge field theory there. But so I'll tell you one short thing about still ideal fluid, and this is 2D, and this is again now something which is really, even though people spent better part of 19th century doing it, it makes sense. So in 2D, when you have this incompressible fluid, which is also potential, so you have velocity x, and you can introduce a stream function in two-dimensional case, so that your Vx will be deep psi dy, and your Vy will be deep psi dx with a minus. But it's a potential flow, so it is d phi dx, and this is d phi dy. And this is Cauchy-Riemann. Okay? And that tells you that in 2 dimensions, your flows have this infinite group of conformal transformation, which means that practically any flow in any domain can be obtained by a simple map of a flow in some kind of a trivial domain, and it's surprisingly practical discipline. And you know why ideal fluid motion is a practical discipline and in which engineering problem it is. Really big engineering problem where you can, not some small bacteria, at small scale, so you can neglect this, but something on a big scale which still works. And what it is? Huh? Rain? Plane? No. When you have planes, you have vortices. These vortices, that's what we'll discuss next lecture, are generated by viscosity boundary layer on a wing, etc. Engineers aren't that into 2D, until graphene and all this.
With the constant profile, yeah, it may not necessarily affect the DA, it's maybe just.
Yeah, well, there are some cases, but I'm not talking about, this is 2D, but this ideal fluid, generally, it's any dimension. It's 3D too. And this ideal fluid means that you can neglect tangential stresses. For this, you need a pressure to be huge. Then you can forget about tangential stresses, and you can do ideal fluid, 2D, 3D, whatever. When pressure is huge. Huh? Oil, but in a very, very American way of handling oil. But generally, how you create a huge pressure?
Explosion?
Of course, you do explosion. So any explosion is ideal fluid. And people actually used it, maybe I have 2 minutes, I cannot resist. In the year 1942, there was a total revolution in the Second World War. The cumulative shell was invented simultaneously, by the way, by Taylor in UK and by Lavrentiev in Russia. And I was actually, I remember Lavrentiev. I grew up and he was teaching fluid mechanics. So what they did, they took a shell which is full of explosives. And what they did, they put here a small metal cone. It was empty inside. Like just a small piece of metal over here. Because they knew, of course, that any explosion is an ideal fluid, and they solved the equation for ideal fluid. So when you explode, it would all turn into focusing jet, very thin jet, of a very, very high pressure hot fluid, which just penetrated the arm of a tank and then exploded and burned everything inside. And that was kind of, and after that, Lavrentiev did fantastic things. For example, he needed 500 tons of a soil moved some 10 kilometers. So what they did, they placed explosions over there, and they computed the potential so that the velocity of this piece will be uniform. So on this, like a kilometer size piece of soil, with a uniform velocity raised up and moved and blocked some cell place where this was dangerous. For Almaty city, there was a dangerous place where you wanted to stop melting snow penetrating. Of course, you can do it by bulldozers in 5 years, or you can do it. Actually, he wanted to use nuclear explosion, and government didn't. I remember how he complained. He says, it would be so beautiful. That would be really. So what I'm saying is that ideal fluid is a very practical discipline. And people who do explosives, they use it all the time as a working engineering instrument. And it means that they solve this equation. So it's practical, just not very relevant to what we'll be talking about, trying to understand what is the resistivity. Okay? So next week we go to viscous and then try to match. Okay? Good. Thanks.
But what is